Hello, my name is Rayan Bapar, and I am a junior at the Woodlands College Park. My app is called NeuroLens, a novel live surgical aid for brain tumor removal intended for surgeons' use. The removal of brain tumors is one of the most difficult surgeries, necessitating utmost precision to navigate the parenchyma of the brain. Yet according to a study published in 2022, more than 25% of neurosurgical cases had adverse outcomes attributable to human error. Current neuronavigation systems only display 2D images of patient anatomy on a computer screen. The surgeon has to attempt to translate them onto the patient in exactly the right position, which can cause a lot of problems. First, surgeons do not have a precise 3D understanding of patient anatomy, only using 2D scans. Second, the risk of damaging critical structures such as vasculature and white matter is high because they can be obscured in brain matter. Many times the tumor is also not completely removed. Finally, the surgeon has to constantly switch perspectives between the 2D screens and the surgical site. Thus, I developed NeuroLens, refined through several prototypes and iterations. NeuroLens dynamically overlays patient anatomy such as the tumor, blood vessels, and nervous tracts onto exactly the right position on the patient, down to the millimeter. The boundaries of the tumor, blood vessels, and nerves are seen in 3D directly where the patient's actual anatomy would be, leading to an unprecedented level of precision, a highly reduced chance of damaging vasculature and nerves, and no need to constantly switch perspectives. The NeuroLens application was built off the Microsoft HoloLens 2 and streamlines all the data the surgeon needs into one application, which the surgeon will wear on their head throughout the surgery, mitigating interruptions and providing easy accessibility. NeuroLens maps spatial geometry and dynamic environments, and also can track hand gestures and use voice recognition. Now onto a demo of the NeuroLens application and how it works. The models you can see are all generated using deep learning. I programmed several of these models using Python, the first being a tumor outlining model. I modified an architecture known as a UNet for 3D and trained it on 300 MRIs. The figures detail the output of my model and the generated 3D tumor for a test patient. For vascular segmentation, I used an encoder-decoder architecture again, but implemented reverse edge attention to account for the tube-like nature of the blood vessels. White matter tracks are responsible for coordinating the most essential cognitive functions, since they correspond to water diffusion, and computed the water diffusion throughout the brain from MRI data, and then utilized a deterministic approach to model its paths. Identifying them in 3D will greatly aid in preserving brain function and preventing damage during tumor removal. The application of the HoloLens is the second main part, coded in Unity, C# as well as C++. I wrote a 6 degrees of freedom tracking algorithm to recognize markers which appear especially bright, and then used image processing algorithms to recognize the markers and generate a 3D reconstruction. I then coded a post-estimation algorithm to superimpose anatomy with millimeter accuracy onto the patient's head. The applications for this project can include any other surgical procedure, as well as preoperative planning and medical training. Thank you for watching.